In this episode, we're going to take the startup of a Linux system and turn it into a clear story you can replay in your head, because most boot questions on the exam become easy once you know what happens in what order and what each stage is responsible for. Booting can look mysterious when you only see a splash screen and then a login prompt. But underneath that quiet surface is a chain of handoffs where one component prepares the next. If you understand the handoffs, you can reason about symptoms like a system that stops at a black screen, a system that drops into an emergency environment, or a system that boots but cannot find important storage. This is not about memorizing obscure details. It is about having a mental timeline that you can use to place a problem in the right part of the process. By the end, you should be able to explain the roles of the bootloader, the kernel, the temporary early user space environment, and the normal user space system that you interact with after boot completes. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. The boot story starts before Linux even begins, because a computer must first decide what to run at power on and where to find it. Modern systems use firmware, which is the low-level software stored on the motherboard that initializes basic hardware and then looks for something bootable. Older systems used a firmware style commonly called Basic Input-Output System, BIOS, while many newer systems use Unified Extensible Firmware Interface, UEFI. And while the details differ, the purpose is similar: set up enough hardware to load the next stage from storage. This early stage is not Linux yet, and it does not know about file systems in the rich way Linux does, but it can locate a boot target and start the next program. The key point for exam thinking is that firmware is the first decision maker, so problems here tend to look like the machine never even tries to start an operating system. Once firmware selects a boot target, it transfers control to a program whose job is to start Linux, and that is where the bootloader enters the story. A bootloader is a small, specialized program designed to load an operating system, and for Linux it often acts like a traffic controller that chooses which kernel to start and what instructions to pass along. You can picture it as the stage manager of a play, because it chooses which cast is going on stage and sets the initial conditions for the performance. On many Linux systems, the bootloader presents a menu of boot options, which might include different kernels or different modes. But even if you never see a menu, the selection still happens. The bootloader understands enough about storage and file structures to locate the kernel image and any supporting files it needs to start the kernel properly. This is a major shift from firmware, because firmware typically makes a high-level choice about where to boot from, while the bootloader makes a more detailed choice about what to boot and how. If a system fails before you ever see a boot choice, you may suspect firmware or hardware detection. But if you see a boot menu and then the system fails after a selection, the bootloader and what it is loading becomes a likely area of focus. Once the bootloader hands off control, the Linux kernel becomes the main actor, and the kernel is the core of the operating system that manages CPU scheduling, memory, device drivers, and the basic rules for how processes and hardware interact. The kernel is not a collection of user applications. It is the foundation they stand on, and it runs with the highest level of privilege on the system. When the kernel begins executing, it starts initializing hardware in a more complete way than firmware did, and it begins setting up the core subsystems it will use to run everything else. One of the kernel's most important early jobs is to prepare a root file system, which is the starting point of the Linux directory tree and the place where the rest of the operating system lives. But there is a catch. The kernel may not yet have access to the drivers and logic required to talk to the storage where that root file system is located. That is why boot is not a simple jump from kernel straight into a full Linux environment, because sometimes the kernel needs a temporary helper environment to get the system ready for normal operation. That temporary helper environment is commonly referred to as an initial RAM disk, with terms like initial RAM disk, initrd, and initial RAM file system, often written as initial RAM file system, init or AMFS. And the key idea is that it provides early user space tools and drivers needed to finish preparing the system. It lives in memory and is designed to be used only during the boot process, not as the long-term place where your system runs. You can think of it like a bridge that spans a gap between the kernel's early startup and the moment when the real root file system is accessible. This matters because many modern systems have storage setups that require extra steps, like unlocking encrypted volumes, assembling complex storage layouts, or loading specific drivers before the real root can be mounted. The kernel can load this early environment and run a small set of scripts or programs to detect devices, load modules, and locate the proper root file system. If that early environment cannot find what it expects, the system may stop and drop you into an emergency mode that feels like a minimal shell, which is an important symptom pattern for exam questions. It is helpful to slow down and define what user space means, because the term shows up in explanations of boot and can be confusing to new learners. The kernel lives in kernel space, which is the privileged part of the system where the core operating system logic runs, and user programs run in user space, which is the broader environment where normal processes execute with restricted privileges. When we say early user space, we mean a very small set of user space programs that run before the full operating system environment is available. When we say normal user space, we mean the complete environment of services, libraries, and applications that you expect after the system has booted. The initrd or initramfs stage is essentially a tiny user space that exists to make normal user space possible. That framing matters because boot questions often test whether you understand that Linux does not go from nothing to a fully running system in one leap. It steps through stages, each one with its own responsibilities and failure modes, and knowing which stage you are in helps you guess what kind of fix is relevant. After the initrd or initramfs environment does its job, the system performs a crucial handoff. It mounts the real root file system and then starts the first process of the normal user space environment. This first process is special because it becomes the ancestor of nearly every other process on the system, and it is responsible for bringing the system into an operational state. Many modern Linux distributions use system and service management based on systemd, which begins with a process commonly named systemd, and older styles used a classic init approach. But for exam reasoning, the big idea is that there is a first user space process that coordinates everything else. This moment is like switching from the construction crew to the building staff, because the early boot tools step aside and the normal service manager takes over. If the handoff succeeds, you begin to see services start, devices become available, and eventually you reach a state where you can log in. If the handoff fails, the system may still be running the kernel, but it will not reach a usable environment, and the symptoms can point you toward root file system issues or service startup issues, depending on where it stopped. A useful way to visualize the entire boot flow is as a relay race where each runner carries a baton and passes it to the next runner at a specific point. Firmware hands the baton to the bootloader hands it to the kernel hands it to early user space, and early user space hands it to the normal user space in its system. In a relay race, if a runner stumbles, you can usually tell at what stage it happened by where the baton is dropped, and the same idea applies to boot. A failure before the bootloader starts is one type of problem. A failure while the bootloader is trying to load the kernel is another, and a failure after the kernel starts but before the real root is mounted is yet another. The exam often gives you just enough information to place the failure in one of these zones, and once you place it, the answer choices become much easier to evaluate. Beginners sometimes try to memorize many tiny facts, but the exam reward is often simply identifying the correct stage and choosing the action that matches that stage. The boot story is your map for doing that consistently. Let's talk about why the bootloader stage is so frequently tested, because it sits at a junction where configuration choices and system recovery options live. The bootloader can select different kernels, pass parameters to the kernel, and sometimes offer options that change boot behavior, which makes it both powerful and a potential point of failure. If a kernel update goes wrong or a configuration is mismatched, the bootloader might still work perfectly while loading something that cannot boot. On the exam, you might see a scenario where a system used to boot but now fails after a change, and the existence of multiple boot entries or a recovery entry can be a clue that you can choose an older known good configuration. The important exam skill is recognizing that the bootloader is not the kernel, and that changing what it loads or what it passes can change the entire startup behavior. Even without touching commands, you can reason that if the boot menu appears, firmware and the bootloader are likely functioning, and the problem might be with the kernel, its parameters, or access to storage. This type of reasoning lets you eliminate answers that are aimed at earlier stages. The kernel stage is often tested because it is where hardware and core subsystems become active, and it is also where the system decides what it considers the root of the file system hierarchy. Kernel problems can show up as freezes, panic messages, or situations where the system cannot continue because it cannot find the root file system. For beginners, the word panic can sound dramatic, but it simply means the kernel hit a problem it cannot safely recover from, so it stops rather than continue in an unknown state. Some kernel failures are caused by missing drivers, incompatible hardware, or incorrect assumptions about storage, which is why the kernel stage is linked closely to the inittrd or initramfs stage. If the kernel cannot access the storage it needs, it may rely on early user space to load additional drivers and perform discovery. Exam questions may describe a boot that begins and then stops with messages about not finding a device or not mounting a root file system, and that is a strong hint that you are in the kernel and early user space region of the boot story. Once you locate that region, you can focus on answers related to device discovery, file system availability, and boot configuration rather than unrelated topics like user accounts or networking. The inittrd or initramfs stage is tested because it is the place where many advanced storage and security features become possible, and it is also the place where failures can look confusing. If a system uses encryption, complex storage layouts, or needs special drivers, early user space is where those pieces often come together so the system can reach the real root file system. When it fails, you might see a minimal environment, sometimes called an emergency shell, and it can feel like the system is half alive and half dead. That symptom is meaningful because it indicates the kernel is running and has launched a small user environment, but that environment could not complete the transition to the real root. In exam terms, the story suggests the bootloader succeeded and the kernel started, but the handoff to normal user space is blocked by something early user space could not resolve. This is why knowing the role of inittrd and initramfs matters. It gives you a structured explanation for what you are seeing. Instead of thinking the whole system is broken, you realize the system is paused at a specific checkpoint because a dependency was missing or a resource could not be mounted. Once normal user space begins, the exam may shift to testing your understanding of what it means for a system to be booted but not healthy. A system can reach a login prompt but still have services failing in the background, and that indicates a later stage issue rather than an early boot chain issue. This is why the boot story should not end at the login screen. It should include the idea that the init system brings up services in an ordered way until the system reaches a stable state. If something fails during that service startup, the system may still feel partially usable, but it may lack network access, user logins may behave strangely, or key functionality may be missing. Exam questions may describe a system that boots but cannot start a certain service or reaches a limited mode, and your job is to determine that the kernel and early user space did their job, but the service management stage did not reach the desired target state. That kind of reasoning prevents you from choosing answers aimed at bootloader repair when the symptom actually points to service configuration or dependency issues. The boot flow story, used correctly, becomes a filter that helps you place any boot-related symptom into the right zone. Another subtle benefit of learning this boot story is that it gives meaning to the word root in different contexts, because root can refer to the root user, the root file system, or the root of the process tree, and beginners often mix these up. In boot discussions, root usually refers to the root file system, which is the base of the directory hierarchy where everything else is mounted. If the kernel cannot find the root file system, the boot cannot continue into normal user space, regardless of user accounts or permissions, because there is no usable environment to apply those accounts to. That is a powerful piece of reasoning for exam questions because it lets you say, this cannot be a user password issue if the system never reached the point where user authentication is relevant. It also helps you interpret prompts that mention mounting, devices, or early environment tools, because those clues are all tied to the root file system being made available. When you keep these meanings separate, questions stop feeling like word games and start feeling like logic puzzles. The exam often rewards that clarity, especially in scenarios designed to distract you with familiar but irrelevant concepts. To wrap this up, the boot flow story is a dependable mental timeline you can use whenever the exam mentions startup behavior, boot failures, or why a system does not reach a usable state. Firmware sets the stage and chooses where to boot from. The bootloader selects what to load and passes control to the kernel. The kernel initializes core subsystems and relies on initrd or initramfs when it needs an early helper environment. And then the system transitions into full user space where the init system launches services and reaches operational readiness. When you can place a symptom on that timeline, you can often eliminate wrong answers quickly because they target the wrong stage. This is especially valuable under time pressure because you do not need to recall every detail to make a good decision. You just need to know which part of the chain is responsible for the behavior described. As you move into later topics, like boot configurations and kernel parameters, you will be adding detail to this same story rather than replacing it with something new. If you keep this mental relay race in mind, you will find that boot questions become less intimidating and more predictable because you always have a structured way to reason about what happened and what must happen next.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.